Welcome to the stats review for Algebra 1. What we're going to do is we're going to go over the types of stat problems you might see on the SOL and give you an idea of how to use them using the technology available to you. So, the first problem is Mr. Tucker gave you a quiz. The following stem and leaf plot shows the scores of students in his class. Round your answers to the nearest hundredth. So the first thing we have to do is we have to convert the stem and leaf into data points. So if the stem is 5 and the leaf is 2, that means 52 is a data point. And 60 is a data point, 66, 67, 69, 71, 72, 73, 74, 75, 80, 82, 83, 89, 91, 92, and 98. So those are the scores on the quiz. So then it says find the mean of the data. Now, the way we find the mean is we add them all up and we divide by the number of scores. But the second part says find the standard deviation using the calculator. So if we're going to use the standard deviation, let's go ahead and go the whole way and do the whole thing in the calculator. So what you would do is you would pull up your TI-84 and you would click on the stat button. And then you would click or select edit. And we go ahead and we put the data in. So 52, 60, 66, 67, 69, 'Now at this point, we want to make sure we have the right data in. So if you see right here, what it's saying is that there are 17 data points. So let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes, so we did manage to enter all the data in. So once we do that, we quit out of the list. Then we go to Stat again, but instead of Edit, we're going to arrow over to Calc and choose one variable statistics. And it's going to ask us what to do. Well, we have our list in L1. We don't have a frequency list, and so we're just going to go ahead and choose Calculate. And the numbers we'll see here is the X bar is going to be the average. And the sigma x here is the standard deviation. So it said round to the nearest tenth. So the average is 76.1, and the standard deviation is 11.8. Because when it says round to the nearest, to the nearest hundredth. Okay, well that's different. So the mean is going to be, and we're going to use a different symbol, because this is the symbol they'll use on the SOL, which is mu, would be, hold on, let me bring it back up, would be 76.1 where'd my calculator go? I didn't crash it, did I? $76.12. And then my standard deviation is going to be 11 points. For goodness sakes. 11.76. Now, calculate a z-score for a student who scored a 67. So the formula for z-score is on your formula sheet, and it says z equals x. I think it's just, actually I think on your formula sheet it's just x minus mu divided by sigma. And so mu was the mean and sigma was the standard deviation. So to find the z-score for a student who scored a 76, it's going to be, I'm sorry, a 67. We'd go 67 minus 76.12 divided by 11.76. And we would go ahead and do that. And if we do that, we would get 67 minus 76.12, z equals negative 9.12 over 11.76. Or a z-score of negative 0.76, because it said round to the nearest hundredth in the instructions. What this number signifies, a z-score, means that the score of 67 was about 3/4 of a standard deviation below the average, because 3/4 is 0.75. So we would say that we're, 0.76 standard deviations below average was the person who got a 67 on the test. All right. Number 2, a data set has a mean of 16.5 and a standard deviation of 3. An element has a z-score of negative 1.5. In which interval does the element lie? All right, so to do that, remember we have our formula. Z equals x minus mu divided by sigma. And so they give us all the information except for x. So we know the z-score is negative 1.5. We know the mean is 16.5. And we know the standard deviation is 3. So now this is just an algebra problem solving for x. So we multiply both sides times 3, and we'll get negative 4.5 equals x minus 16.5. Add 16.5 to both sides, and we'll get 12.5. So in which one of these intervals is 12.5? So this says x is greater than or equal to 10 but less than 13, and 12 would certainly be in there, so that is the right answer. I'm sorry, 12.5 is in there. It's not in B because x is greater than 13. This interval is between 13.5 and 16.5. The number 23 is removed from the data set, and a new box and whisker plot is drawn. Compared to the values in the original box and whisker plot, describe the changes to each of these values: increases, decreases, or stays the same. Now the key here is this. It says that no number is repeated. If no number is repeated, when we eliminate 23, I know that the new max is going to have to be some number less than 23. So the upper extreme will decrease. But the lower extreme here is not going to change. Me eliminating the value of 23 is not going to create a new lower value. So the lower extreme stays the same. Now the key here is that no number is repeated. So if no number is repeated, either this value here for the third quartile was a number or the average of it, two numbers, one lower, one higher. So everything's going to get moved back to 1. So the upper quartile will decrease. The median will decrease. And the lower quartile will decrease. Because remember, we find the quartiles by putting all the values in order. The median is that middle number. So if we take the top number away, then the middle number will be shifted down slightly. We don't know how much with the data set, but we do know it's going to decrease because no number is repeated. All right, each of the box and whisker plot represents a data set with 11 distinct elements. Circle the letter of these statements about these plots that appears to be true. All right, so for A, it says there are more elements in the lower quartile of plot B than in plot A because the left whisker plot of plot B is longer than the left whisker of plot A. All right, first of all, this cannot be true because it says the number of elements. Each data set has 11 elements. So if we divide that up into fourths, which is what the quartile is, each one is going to have the same number of elements in each quartile. So A is out. Since both data sets have 11 elements, the box of plot A and the box of plot B contain the same number of elements. Let's come back to that. There are fewer elements in the upper quartile of plot A than plot B because the right bus, see once again, same number of elements. We know that one's out. The interquartile range of plot A is greater than the interquartile range of plot B. So first we have to know what interquartile range is, also known as the IQR. And the IQR is the third quartile minus the first quartile. So for plot A, that's going to be 19 minus 8. So the IQR equals 11. For plot B, that's going to be 21 minus 11. So the IQR for this one is 10. So the interquartile range of plot A is greater than the interquartile range of plot B. So that is correct. But be careful, it said circle the letters of the statements that appear to be true. So there might be more than one answer. So plot A and plot B is, I'm sorry, so that is true. So let's look at E. The range of both plots are equal. Well, the range is simply the max minus the min. And if we look at them, they both have the same maximum and they both have the same minimum, so they are both going to have the same range. Now let's go back to B. Since the data set has 11 distinct elements, the box plot of A, the box of plot A, and the box of plot B contain the same number of elements. Now the only way this could not be true if some data points were being repeated, but it tells us there are 11 distinct elements. Oops, sorry, my smartboard calibration's off there a little bit. It tells us that there are 11 distinct elements. And therefore, that's true. There does have to be the same number of elements in each one, so B is also true. All right, the data set shown has a mean of 37 and a standard deviation of 6.3, round to the nearest tenth. How many data points have a z-score greater than 0.2? So, what value does a z-score of 0.2 refer to? So remember, z equals x minus mu divided by sigma. And mu is the mean, and sigma is the standard deviation. So, 0.2 equals x minus 37 divided by 6.3. So we're going to have to multiply both sides by 6.3. And I get 1.26 equals x minus 37. Add 37 to both sides, and I get x equals 38.26. So, what are the data points that are greater than 38.26? That one, that one, that one, that one, and that one. Those are all greater than 38.26. So the correct answer is 5. This table shows data on the number of dollars raised during a fundraiser for 4 different classes for 1 student in each class. So what we have here is this is the mean for the entire class. And this is the standard deviation for the entire class. So what they're really asking us to do is to convert Jill's z-score into an actual number, Kelly's z-score into an actual number, Monroe's z-score into an actual number, and Tim's z-score into an actual number. So let's do Jill first. So for Jill, it's once again z equals x minus mu divided by sigma. So for Jill, 1.8 equals x minus 60 divided by 11. So we multiply both sides by 11, and we'll get 19.8 equals x minus 60. Add 60 to both sides. And we'll get Jill. Jill actually raised $79.80. Then we repeat the process over for Kelly. Kelly's z-score was 2.1, but her class average was lower and the standard deviation was higher. So what does that result in? Multiply both sides by 2.1. I'm sorry, by 12. And we will get 25.2 equals x minus 58. Add 58 to both sides, and we'll get $83. Oops, sorry, that was Kelly, wasn't it? So Kelly raised $83.20. And we can do the same process over and over again. If we do it, we'll get, for Monroe, we'll get $73.20. And for Tim, we'll get $82 even. And so the person that raised the most money is Kelly. All right, the mean for a data set is 45. The z-score for the data point is 0. The z-score for data point B is 0.2. What are the possible values of data points A and B? Now this confuses a lot of people. Remember that z-score is how far above or below the average you are, measured by standard deviations. So a z-score of 1 represents 1 standard deviation above the mean. They didn't give us the standard deviation here, but they did give us the mean. So a z-score of 0 means that your actual mean is 45. So the correct answer is either C or D. Now, the second z-score for B is 0.2, which means that you're going to be 0.2 standard deviations above the mean. So the only other set that has a data point above the mean is C. 44.2 is below the mean, that can't be the right answer. A data point has a mean of 68.42 and a standard deviation of 7.91. An element in this set is 64. What is the z-score for 64? So once again, this is a simple one. X minus mu divided by sigma is the z-score. So z is going to equal 64 minus 68.42 divided by 7.91. So z is going to be negative 4.42 divided by 7.91. And if I do that, that equals negative 0.55878636464 in the calculator. But it tells us to round to the nearest hundredth, which is the second decimal place. So that is going to be negative 0.56. And that means that the score of 64 is 0.56 standard deviations below the mean. The data on annual rainfall for 32 cities is summarized in this histogram. The mean amount of rainfall in these cities is 32.5 inches. The standard deviation is 4 inches. On the histogram, circle each interval that may have a data point 1.5 standard deviations within 1.5 standard deviations of the mean. So, 1.5 standard deviations of the mean is going to be 1.5 times 4, or 6. So the mean is 32. So all points that are 6 above is 38, and 6 below is 26. So this, and this are all bins in the histogram that could contain values within 1.5 standard deviations of the mean. A lot of this is understanding what a histogram is. A histogram is like a pile. So if I have any values in annual rainfall between 26 and 28, I put them on this histogram. So right here, this represents 3 values between 26 and 28. There are 3 values between 28 and 30. There are 5 values between 30 and 32. But it's just asking us which ones are between those values. So the ones I put X's on are the ones that you would select. A set of data for the number of points in a basketball team earned for each of 9 games in a tournament is shown. The mean for the data set is approximately 80.1, and the standard deviation is 4.1. Using these approximations, which scores are within 1 standard deviation of the mean? So within 1 standard deviation, the mean is either 80.1 plus 4.1, which is 84.2, or 80.1 minus 4.1, which is 76. So any value between 84.2 and 76 is within 1 standard deviation of the mean. That's those 3. All right, last problem. This is a tricky one. This one is really getting into how quartiles are found. So Team A scored 14 points and scored a different number of points in each of the team's 14 games. Team B scored a different number of points in each one of their 13 games. So here for Team A, they scored different points in 14, and their median is right here at 60. So that means that there are going to be 7 values above that and 7 values below that. For Team B, it's a little bit trickier. Because there are 13 values, there will be one value that is exactly the median, 6 values above, and 6 values below. Which means that when we find the quartile, there will be 3 values here and 3 values here. So what is the number of games that Team A and Team B scored 60 or more points? And the answer is 10. Thank you, and I hope you feel prepared for the stats portion of the AP exam.